go ahead and get started here. It's the last week of class, and I figured what I would spend today's lecture on is just reviewing some of the key concepts of previous lectures, and just put a little preview of the final exam together so that you feel comfortable going into it. I thought we'd just kind of do a mix of some of the solar thermal and some of the wind that we've covered. Make sure that you're comfortable with the things. Use this as a little bit of a Q&A. I'll probably throw a couple questions out there just to make sure that you're familiar with some of the concepts and symbols. So what I'd like to do, I'm just going to get a kind of a fresh sheet going here and put a rough outline of the questions you can expect to see on the exam. And then I've got one other, kind of a big picture problem that I think is relevant to a lot of the solar thermal projects that you guys have elected to do for the course. Kind of going forward, if this is something that you want to get serious about down the road, or if there are some big federal initiatives or state initiatives or whatever to actually put a cost on carbon. I think that's happening in other countries. If it comes down the pike where, hey, I've got a proven technology here that I can demonstrate is carbon neutral, maybe down the road some of these big carbon producing companies might actually pay you to do it, might actually subsidize you to do it. I mean, things like this have happened in other states, they're happening in other countries, and they might happen here down the road too. So I want to do a problem like that as well. But for now, this is lecture. I also want to spend a little bit of time seeing how your projects are going as well. So I'm just going to call this lecture 27 because it's week 14. And this is just going to be final exam. I guess it's a preview, not really a review, so we'll just sort of do a preview. Okay, so one question that I certainly want to make sure that's clear for the solar thermal and wind course is some question on Bett's law. Now, I haven't written the exam yet, but tell me one thing that you kind of remember from Bett's law.
16/27.
Okay, there's a good one. 16/. And what was 16/27?
The theoretical maximum of a wind turbine.
Okay, and I think when we derived that in class, we went through a lot of the initial stuff. At the very end of that derivation, there was kind of a nasty derivative, which I don't expect you to know, but I think we got most of the way towards it. Joe, what was something you kind of remember from Bett's law?
Pass?
Or what it had to do? Yes, wind passes through the turbine. But do you remember what this number was, 16/27 in general?
Well, isn't that that's the efficiency?
It's the efficiency. Yeah, that's right. It's the theoretical max efficiency. And I'll write this guy. Not to put you on the spot back there, Dustin. But do you know what this little scribble is I made right there? It's terrible. Let me try it again.
Is it Tony? Yeah, it's the Greek letter H.
Yeah.
What it's called?
Yeah. Do you remember that, dude? Is that what that is? It is the Greek letter H, but how do you remember how to pronounce it in Greek at all? Covered a little bit in, well, it has a little bit to do with there's a Carnot efficiency as well. And so it's the symbol for efficiency. Does that ring any bells at all?
Yeah, I have that. I just don't remember what it's called.
Okay. It's called eta. And I guess that sounds a little bit like H. Okay, so that's 16/27, max efficiency, 8 is a symbol. Now, one key concept that I'm hoping you come away with, and we talked about this before, and it's got a lot to do with conservation of energy. And almost any one of these systems, you can't violate the first law. And another portion of the conservation of energy is that it's conservation of mass. And it just means that you're going to have mass coming in the front end of your turbine. Guys, what's the dot mean? Anybody?
Time component.
Time component, time derivative, the change with respect to time. You're going to have some mass flow going in, and you're going to have some mass flow going out. And we know that the mass in has to equal the mass out. There's no antimatter machine in the wind turbine that's making the mass disappear. Another thing to consider is that you've got the velocity going in, and you've got the velocity going out. And which of those two velocities is going to be greater? In's going to be greater, out's going to be less. Couple other things to consider. When we derive this, I think we use the symbol S for the area, which is a little bit unconventional, but you can sort of think of this as the surface, the frontal surface area of the turbine, if you will. You can also think about a control volume here, sort of an area in, and back here somewhere is an area out. Now, and just going back to velocity for a second, what's the velocity symbol that we used for the within the turbine itself? Do you remember that guy at all?
V bar.
It was V bar, and what does that mean?
The average.
It's average. Okay, good. And so, and the way to write that, it's just like you're going to write any other symbol. There's the application of algebra is the velocity in plus the velocity out over 2. So those are the key components to, and I think we also said that the velocity out is going to be less than the velocity in. I think that's also a pretty key component. What else am I kind of missing from this thing? What might be important that you might want to know to calculate the power or the energy in the air?
The density.
Yeah, you'd want to know the density. And so upstream here, you've got density in. Anybody remember what that funny looking P is? Rho. Okay, cool. And then here's rho out. The other thing to consider is that rho in is going to equal rho out. And now that is somewhat of an assumption because obviously, well, maybe not so obviously, when this air hits that turbine, and I've just kind of drawn it as a disc, but if you want, you can sort of put some blades in there. I mean, they're spinning obviously, but if you took a picture of them, they'd be there. When that air molecule hits that turbine, it does become a little more dense locally, but it's not like the turbine itself is affecting the density of the atmosphere. Overall, the turbine isn't making the atmosphere more dense or less dense. It's just hanging out there in the breeze. So the density in also equals the density out. So those are the key components. What I'll probably do is throw at you some kind of wacky designed wind turbine. Like your cousin comes up with something. He's I've beaten Bett's law. I figured it out, and I'll leave it up to you to sort of figure out where his error in reasoning was. Like, oh, Barney, you got more mass coming out than you got going in. That was your mistake. And that's why you've got 25 27s instead of 16 27s. So is that a good, you got your notes on how to derive Bett's law and all that, so.
I mean, yeah, sure.
Okay, good, okay.
Can't read them.
You can read this though, right? I mean, my handwriting's okay there. It's the V's, the rhos, the etas. Maybe I'll just write rho over here. It's RHO. And then you know what density is, velocity, mass. Okay. Okay. And in the presentation I gave, well, you guys remember. Okay, another thing that I'd like to test your knowledge on is Bernoulli's equation. And we went through it. And do you remember what Bernoulli's equation was an example of? Like which law?
Carnot's? No, Bernoulli's, it's air.
Yeah, no Carnot. Carnot's almost exclusively for combustion. It is, yeah, the dimensions are going to be energy per unit volume on both sides of the equation. So if you got energy per unit volume on the left, energy per unit volume on the right, what's that an example of? Yes, it's the first law. It's a conservation. So first law, example. Conservation of energy. And it's going to be applicable to both solar thermal. I'll just write ST for solar thermal, and wind. And then do you remember there were three different components. Do you remember what the three energy components were?
Strain, kinetic, and potential?
I think that's right. Strain, kinetic, and potential. Is that making sense to you at all?
Yeah, I
Right.
just don't have the strain.
Okay. The strain can be a little bit weird, and let's take a look at strain. Yeah, it is.
Is that the M over V? No.
Bernoulli's equation. Let's just bring it up here. Yeah, the kinetic and the potential I think are pretty straightforward. You get beat over the head with that in NRG 101. But let's look at the strain or the pressure energy just for 1 second. And I'll give you what I hope is a pretty concrete example of what I mean by that. So do you guys understand this first one? It's 1/2 mv squared, except instead of m, we've got rho because we've just divided by volume. And so it's energy per unit volume. Is that, okay. And then the rho GH looks a heck of a lot like mgh, but again, you just divide it by volume, and there you go. Okay, so let me just let's look at this guy for a second, because it can be a little strange. No pun, well, Maybe no pun even made, I don't know. So I don't want to, I'm going to just label this as 3, but I won't necessarily give you a question on what strain energy is, but I think it's important that you understand what pressure is. So let's do that for a second. Pressure. Now, and I think I've mentioned this a time or two, but is pressure an intensive or an extensive variable? Pressure is intensive. Pressure is similar to temperature. It's similar to density. It doesn't matter how much you have. Like, so for example, you bring a barometer into this room. It doesn't really matter how big the room is. You know, we could just wall off a little chunk of it. As long as we don't squish it, the pressure is going to be the same. So, you know, first of all, the thing to think about is that it's intensive. Next thing to think about. Let me write it out. Let me do this fun little thing that I frequently do so that I can show you that pressure is in fact energy per unit volume. It ties a lot of it ties energy together with other physics. So what are the sort of when you would define pressure, what kind of units would you give it in? Force per area is the like PSI, megapascals, et cetera. So it's going to be force over area. And so these little brackets here, I'm just sort of saying that the dimensions of pressure are force per area. Now, what are the dimensions of force? And what Newton's second law, what would you do there? Mass times acceleration. So I'll write that as mass times length over time squared. And then what are the dimensions of area? Meters squared, so length squared. Length squared, there we go. So now we can just kind of pop all this in here and say that pressure, okay, is force over area. So I'll get my mass times my length over my time squared over my L squared. And that ends up equaling, I'll just simplify it, mass over length time squared. Now, let me just do another little a little trick here, and I'll kind of wall this off on the sheet for you. I'm going to do a little trick off to the side. Now, if I just take force over area, and now you know from algebra that as long as you keep multiplying something by 1, it doesn't change. But there's a lot of different flavors of the number 1. It could be 10 divided by 10, it could be pi divided by pi, whatever. It could be 5 plus 1 divided by 6. There's a lot of different flavors. There's infinitely many flavors of 1. So I'm just going to use one flavor of 1 and multiply it by length over length. So, force times length, force times length. How do I show you that guy? Force times length, MGH. Well, off the top of your heads, you know what force times length is? Not velocity. velocity. Velocity is just length per time. If that were the case, then force would have to be 1 over time, which it's not. This is actually very, very critical. I know we covered this in 101. I know it's been a long time, but force times length. How do I get that guy across? Let's do it this way. Get one more little sub. Well, I can do it here. I can do it here. Force times length, and it's basically already on the page. So if I take a mass right here and lift it up to right here, I know that the mass has a weight that's sitting in gravity. We're doing this experiment on Earth, not in outer space. The mass has gone up. Gravity is sitting over here, pointing down. And gravity itself, get one more little guy over here. Gravity itself has the dimensions. Well, you know it's acceleration. So that's just length over time squared. So what I've done is I've lifted this mass some height h, right? It's gone from here up to here, and that's the height h. And what are the units of h? Just length. Very easy. Okay. So I've got mass times gravity times h. Which two components of these three guys? And I've got these three things hanging out. I've got the mass, the height I lifted it, and the gravity. Which two of those can I combine to make a force?
The height and the mass?
No.
Gravity and height?
No.
Gravity and mass.
Yes. Yeah. So in this case, the force or the weight just equals the mass times the gravity. So from there, and we already knew that. It was sitting right over here. There's the mass and there's the acceleration. So gravity, acceleration, same thing. Okay, so we've got that the m and the g are a force. That should just tell you right there. There's the F we've been working on. What's the one remaining component? H. What's H? Well, it's got a dimension of L. So, back to my original question. Multiplying the force times the height, or the force times the length, you know that I've moved that mass up. What is force times length? What have I done to that mass when I lifted it?
Potential energy?
Yeah, exactly. It's just energy. Force times length is energy. And I use an example where I was lifting something up, but it's the same as if I've got a block sitting here on a pad and you're pushing it along. You're pushing in this direction, and let's say you're going to push with 50 pounds of force or whatever, and you're going to move it 10 feet. The amount of energy required is how hard you pushed times how far you moved it. Doesn't matter if you're moving it up, down, left, right. That's energy.
One's potential and then the other one is what you use kinetically?
Well, that's a great question. If I'm doing this, it's usually just called potential energy. Because if I'm doing it in a gravity field, I can get that back. It's just, I throw it up, it's gonna come back, right? Every bit I put in goes back. But if I do this, I need something bigger, better props. If I do this, push it sideways, that's called work, because I didn't get it back. I gotta do the work again. Oh, God, that's a lot of work. So work and energy are really, they have the same dimensions. Energy, you kind of get back if it's gravitational or if it's a spring. Work, you don't get it back. Maybe you get paid to push the thing around, but that's that. Okay. So, long way around of saying that this equals energy, and what's area times length? It's an easier way to say that. Volume. Perfect. Okay. So hopefully we've kind of dug to the bottom over here and found out that pressure is energy per unit volume. And we did a little bit of that in the practicum last year. We bought an air compressor and said, okay, how can you store energy? Well, you can jack up the pressure inside your air tank. And, well, how much do you have? Well, multiply the pressure times the volume, and that's how much energy you have. It's kind of wimpy. It's not very dense, but if you've got an abandoned salt mine somewhere, you could, conceivably put a lot of air down there in a big volume, and with, relatively small pressure change, you might store some energy. Okay, pressure is energy per unit volume. Now the strain bit, I'll briefly explain that. I don't foresee having this particular thing on the exam, but I do want to just tell you briefly what strain is. This might be a bonus question. Strain is when, and this isn't just casual, I strain my leg or I feel strain. This is a technical term, technical engineering term. And what it means is that you've just got some chunk of matter with some initial length, we'll just call it L naught, and you pull on it with some force. You got to pull on it in both directions. And what happens after you have strained it is it gets longer. Could be metal, could be wood, could be nylon, could be a wind turbine blade spinning around. And that's typically why wind turbine blades are thicker at the root, right? Because you need more. If you made a little tiny skinny root of a wind turbine blade, it's going to bust off. It's going to fly apart because it's not built properly. So strain, and here's what we're looking at. There's just some delta L, some change in length. And strain is simply, and this is, I'm going to use the symbol epsilon. Strain equals delta L over L. Now, knowing that, what are the units or dimensions of strain? Kind of a trick question.
L?
Well,
In meters?
well, let's say you measured delta L in meters, and let's say you measured, sorry, I need to put L naught there. Let's say you measured L in meters, you had a big rubber band, and maybe L naught was a meter long, and then you stretch this rubber band 10 centimeters. So you're dividing, or 0.1 meters. So you're dividing 0.1 meters by 1 meter. What are the dimensions there that you're left with, or units?
Good. I always imagine strain being like how hard you're pulling, so.
Well, we'll get to that in a second.
Be in PSI.
We'll get to that in one quick sec, but let's do strain first.
If it's meter over meter, then they cancel out.
Exactly. So strain is dimensionless. Doesn't have any dimensions at all. Now, the flip side, I think this is where you're going with that one, Ryan, is this other notion of stress. Now, I've shown you that I've pulled on this bar or rubber band or whatever you want to call it with some force F, and I'm going to try to sneak in a third dimension on us here. If I can just kind of turn this guy into like a, I don't know what this is, a semicircular prism, but it's got some cross-sectional area A, so that the thicker this rubber band is, the bigger A is. Stress, sigma, lowercase sigma, equals force over area. And I think that's where you're going, Ryan, with the PSI. And kind of the cool thing, and we just covered this a second ago, is that pressure is energy per unit volume. We also know that pressure is force per unit area. And I just got done telling you that stress is also force per unit area. Why do we need both of those? Why would we need pressure and stress? Yeah. Stress is a little bit weirder. I'm just going to throw a little picture out here. I don't want to beleaguer it, but pressure. And you can go back to your notes here. And maybe I'll just kind of draw it this way. Pressure is going to be kind of the same in all directions. You see that, when you go and read your barometer in the morning, you say, oh, it looks like we're at 30 millimeters of mercury or whatever. No one's ever going to ask you, what direction is that pressure pointing? You might say, which direction is the wind blowing? Oh, it's coming from the northwest. But no one's going to say, oh, what's the direction of the pressure? Now, that is the subtle difference between pressure and stress. I think that's where you're going with this, Dustin, is stress does have a direction. In our little example here, this was just a one-dimensional example of stretching a rubber band in one direction, but you could also imagine, pulling the rubber band front to back or side to side, sort of pulling it apart, twisting it, bending it. So stress is a little stranger in that it'll have a x component. I'm going to do two x's, and I'll tell you why in a second. It's going to have a y component, and it's going to have a z component as well. The other thing to note is, in addition to stretching something in all three dimensions, so already you can see that stress is more complicated than pressure, because we're talking three dimensions already. The other thing to keep in mind is that I can come in here and I can take the material and go like this. And so similar to how we were just talking about work being sort of a sliding thing, you can see that I could take something and put an upward force on my right hand, a downward force on my left hand. I'm forcing it over this area, and that's also a stress. It's force per unit area as two surfaces slide past each other. It's a lot like friction. Yeah, it's sort of like, it's friction that holds something together, right? It's sort of, friction that, if I glue these pages together, there'd be more friction, the thing wouldn't bend. So yeah, it's exact, and it's just molecular forces holding the solid together. So I'm also going to have a, it's getting a little crowded in here, but this is going to be a sigma xz. This one's going to be a sigma xy, And so these are little arrows that are in that surface. There's sort of like, the first three I drew are sticking out of the surfaces. The two that I just drawn are like actually drawn on the surface of that cube. This guy is going to be, over here is going to be sigma z y, and this one is going to be sigma z x. And it gets kind of weird, but I just want to kind of show you the whole nasty beast. This one's going to be sigma y z, and this one's going to be sigma y x. So I've drawn three normal, and those three normal ones are the double subscripts, the XX, the YY, the ZZ. Those are the ones you think just pulling the thing apart. And then 6 shear. And those are the kind of the three ways that you could sort of rip something apart. So whereas pressure just has one component, points it's the same amount in all directions. Shear actually has 9 components. Stress has 9 components. 3 normal, 3 shear. Same with strain. So that's a long way around saying what the heck is strain energy? Well, that's what it is. It's the energy of deforming the material. So back to Bernoulli. So hopefully I've kind of answered that little question there. Strain/pressure. Any questions at all on that? I just want to take a little break here, and then we'll get on to a couple more. Good. Okay. So we got a one Betz law, one Bernoulli's, and then I might throw a little bonus question out about the stuff we just now talked about.